Hi guys, welcome to my introduction to functional programming in Haskell. I've got about 150 slides, so hopefully we can get through this really quick. This is a little bit about me. I will actually add links into my slides about things that I think are related and important. I also have a lot of links in my GitHub account that I just didn't have room to add to these slides, so just a really quick introduction. This is 200 for a reason. I've got a lot of slides and I'm going to be going really fast. I'm also going to be introducing concepts just to illustrate a point without really explaining to them. I'll kind of give a hand-waving explanation, and I'll probably go back and explain it later. And this is meant for programmers who already have some programming experience, not necessarily in anything functional, but either Python or Java is perfectly good. So these are a lot of resources that I like to use when learning Haskell or introducing people to Haskell. These are I use a lot of examples from these resources when building this. So lots of thanks to the people that wrote these resources. Thank you. So people can read this slide in two ways, I think. It can be either, yay, Haskell, pure, yay, lazy, static, monads, or, oh god, Haskell, pure, monads, right? And I'm here to try to convince you that actually all of these things are very good, and what make Haskell a excellent programming language to work in. So I'd also like to say that Haskell has been extremely influential in terms of both influencing different programming languages and also with its use at some quite well-known companies, and that I think Haskell will continue to be highly influential in the future. So we'll see. Also, that Haskell is a factory of new ideas in the sense that a lot of things that we take for granted in certain languages were actually from Haskell, and actually one that's not on here is actually both list comprehensions and indentation sensitivity, which are both features in Python that were actually lifted directly from Haskell, and Mr. Guido van Rossum has thanked the Haskell community for those ideas. So lots of great cross-pollination happening. I'd also like to speak about how Haskell is actually extremely valuable to both me and I think to many people, and that we really don't have to say much other than to show some of the things that have been built with Haskell. So we can talk about how Haskell is not a hair shirt. Instead, I use it as a secret weapon. And maybe that wasn't the case a couple of years ago, but it's definitely now the case, now that Haskell at least has reached a significant minority of people that have created a large, high-quality base of libraries. Erlang's been like that for a long time, but Haskell, especially in the last 5 years, has especially risen out amongst all of the academic languages, I would say. So before we get into the meat of my conversation, I'd like to very quickly show an example of some of the tools that we actually have available for Haskell. And so this is a website called FP Complete, and they actually have a web IDE with quite a few examples. Here I'm actually cloning one of the examples, and here we are in the web IDE. And it's exactly like you would expect. There's some code, and you can edit it, and there's a little play button with a link to the website. And here we go. We have Fibonacci as a service, so that works very nicely, very responsive. You can do all sorts of things with the Markdown editor. Very nice example. Very nice ID. You can try these examples out without even having an account. It's very nice and fun to play around with, and a great way to get your feet wet in Haskell without having to download a single thing. So definitely check that out. I'd also like to say that I'm spoiled by Haskell. Actually, I've been using Haskell for quite a while now, and whenever I'm not using Haskell, I really wish I was. There's a lot of features in Haskell that I really miss, and I do give up certain things in terms of library availability, which really I haven't really found a library that I really missed in the Haskell ecosystem, but just there are less libraries than the more mainstream communities, and the community size is smaller. But what I get back is a fantastic language, and actually the even though the quantity of libraries is lower, the quality is probably the highest I've ever seen in any of the programming language communities. And so I really miss Haskell when I'm not using it. And in the previous slide, I actually said learning its ways pays back in spades. And in most other languages, learning its ways is a pretty arbitrary and tedious kind of experience where you're having to memorize a whole series of corner cases in the syntax of the language or something like that, or the data structures. And even though there are some irregularities to the way that Haskell does things, like I wish Haskell's numerical hierarchy was a bit better, ring, group, all that kind of stuff, but it's all hidden away by num, and none of that matters at this point. But what I'm saying is that a lot of things in Haskell are not very arbitrary. Actually, they're very similar to what you would expect straight out of math class, where the Haskell has a large amount of influence from mathematics, like you would expect from a programming language. And learning its ways means that you're learning, I think, some rather substantial, deep computer science, and not really just another sugar coating over some C++-like language. I'd also like to say that I'm self-centered in making this presentation, in the sense that I hope that this will give more people the feeling that they can actually dive into Haskell, and that it's useful and valuable to them, and to create cool things. There's already so many cool things that have been written by the Haskell community, and I think it's going to keep going, and so hope to see you here for the ride. And that's actually exactly what I mean, because hope you get on the ride pretty quick, pretty soon, because if you don't, you might be a little late, and you might have to learn Haskell in a hurry, because now it's the thing to learn, and I think it'd be much better if you took the time to learn Haskell at a leisurely pace rather than have to hurry and learn it on a deadline. And I'm really glad I learned it, because it's really significantly changed the way I've think about programming. So here's a nice graph made by Red Monk. They do language rankings where they take the Stack Overflow tags versus the number of projects on GitHub. And as you can see, it kind of naturally forms a first world, second world, and third world of programming languages. And actually, this third world goes on for a long way. And as you can see, like you would expect, you have Java and PHP and all the really popular languages. And then right on the cusp of the second world, you see Haskell, right? I can't quite call it a first world language, even though Scala and R, I could say, are definitely in the first world. But as you can see, Haskell is nestled at a really nice point in the programming language popularity graph, or at least here in this one. I think that this one's a really good illustration of the territory, at least at this point. And so I think that illustrates a good point. You can see Swift and F# and some other languages, and that I think Haskell is actually going to eventually merge into here, probably more likely than any of the other languages that are near it. So we'll see. And if there's one thing, just one, that you can take away from this screencast is this slide. And so this is kind of a dense slide. There's a couple of lines on here, but probably the most important thing is this CPUs. The number of CPUs has risen. Now, if we look at the clock speed here, can you remember being around in 2004 and saying to yourself, "Oh man, I can't wait until 2015 when we're gonna have 15 gigahertz CPUs and it's gonna be great, right?" But as you can see, that quite never happened. Actually, the laws of physics, mainly the speed of light and the propagation of electrons through different materials, has limited the clock speed of CPUs. And so now, instead, CPU designers have done actually two things. First of all, they focused more on low power CPUs. There's been a seemingly a dip in that, or an exploration back into the lower power zones, but also an increase in the number of cores in CPUs to accommodate the new fact that Moore's law is breaking down. Actually, I'm certain that eventually this line, the number of transistors, will eventually flatten out because we've gotten to the point where the wires and all these parts are only atoms across, so we really can't fit all that many more transistors into a specific die. So how CPU manufacturers have been doing, and this is what they're going to continue doing, is that they're going to radically simplify the CPUs. We've been doing a lot of pipelining and massive cache hierarchies to try to eke out the amount of performance, but that's going to stop. They're going to rip out all those things, make very simple CPUs, and throw in lots of CPUs, lots of cores. And so not only that, but that's also going to mean that clock performance is probably going to go down as well. And if you are programming serial programs that aren't parallel, essentially your performance has not only flatlined ever since 2004, it's possibly even going to go down. So you're going to have to adopt a programming paradigm in which is the programming paradigm is able to capture computation over many cores, massively multi-core computers, and Haskell is extremely well poised for that. So we'll see. And to kind of drive that point home, I'm going to say that purity is the right default. When you have a program that the compiler cannot think about the resource utilization efficiently, then especially across multiple cores, which very few, if any, compilers are even adequate at doing that today, then essentially your performance is going to degrade the more and more cores there are in computers. And so to be able to think about these kind of things, resource allocation, cache coherence, we're going to have to adopt purity, because it's much more easy for compilers and compiler writers to reason about optimizations and rewrites and all of these problems when we're facing a massively multi-core future. And that's only one reason why purity is the right default. We're going to see again and again why purity is the right default, and why laziness is arguable whether or not it's the right default, but it is across the community agreed that purity is guaranteed the right default, and we'll see that. And I'm here to say that OOP is much harder than pure functional programming. Pure functional programming is actually quite easy compared to OOP. I mean, this is a joke, but it reflects reality. There are some very crazy things, like even in very common applications like Swing, and that most of these design patterns are actually, as Norvig would argue, a demonstration of the weakness of the language and its lack of abstraction, and not a necessary design principle. So and I would agree with him on his points. So, and I'd like to say that there's a lot of reasons why it's actually even easier. The first one is that after you've written your program, maintaining it with a strong static type system is much easier. And this is a really, really big selling point, especially for large code bases. And that the other thing is that when you're thinking in a pure functional paradigm, you don't have to keep this massive implicit state of everything else that's happening in the world. All you're thinking about is the inputs of your function and then some mapping to an output, and that's it. There's all of the context is explicit in the arguments to the function, and this is another very big win. As well as that when you have a strong enough static type system, you can actually create special types to restrict the possible computation and thus make illegal states unrepresentable. And this is very important for maintainability as well as even optimization, and just very useful across the board. Many of these things in Haskell are, when combined together, are actually greater than the sum of the parts, and I'll try to convey that as much as possible. As well as that with an advanced compiler, you have the compiler doing a large amount of work for you rather than you having to caress and work with your code to make the compiler happy. You're actually by embracing an advanced compiler, you have the compiler do a large amount of things like optimization that you would have to do manually otherwise in other compilers. So many, many big wins. And I'm also going to argue, actually, that OOP is ill-defined. Most of the time, the definition of OOP is the reference implementation, and where there are actually simultaneously conflicting definitions of OOP, and most of what people think about OOP is based off of C++, essentially stealing Simula's classes to make C++, and then Java adding garbage collection and runtime checking, and then Python taking it a step further. So nowhere in any of this was there a formal definition of what object-oriented programming is. It was simply just an accretion, a gradual process. And while pure functional programming is actually very well defined, and this is very important when you want to convey very difficult concepts across large teams of programmers. If your language of choice is only defined as what the compiler does and not a well-understood set of principles, it's going to be very difficult to move a project forward after it gets very large. So, as well as that, there's some really good critiques of Haskell. You know, Haskell isn't perfect; it has its warts. But there's also some really bad critiques of Haskell, and an example of that is that there was an individual who created a micro benchmark where he was testing C versus Haskell, and the idea was to make a bit array. And so, very trivial to do it in C, and in Haskell, the default way, or the way that seems, or not obvious, but at least working with lists and integers, he created a program that actually at runtime created not a bit array, but a linked list of arbitrary precision integers, and then created a benchmark and ran the two of them and said, oh my gosh, Haskell's hundreds and thousands of times slower than this bit array, and said, haha, Haskell is tesukors, and basically what happened is that the Haskell community responded and said, hey, wait, no, actually this is a proper implementation of a bit array, and it's just as fast as C. And I think he eventually did become a Haskeller, so there are honest critiques about Haskell, but there's also bad critiques of Haskell. So we want to avoid these really bad critiques, and it's pretty easy actually. It's not hard, and that as much as I like to bash object-oriented programming, there's been a lot of very healthy cross-pollination and bridge building happening, mainly in Link and it's the STM, where some ideas from Haskell cross-pollinated over to the OOP world, and now some ideas from the OOP world are coming back into Haskell. So it's really been a great thing that both sides have been able to work out, and lots of interesting stuff has come out of it. And so I'd also like to say that Haskell is a very it's first of all an industrial strengths compiler, in the sense that it's able to create very large and complex binaries and very efficient ones, as well as that there's a lot of both theoretical and pragmatic changes that have happened in the compiler. So one of the big pragmatic changes is the new I/O manager, and what this does is that this essentially means that the Haskell runtime now linearly scales to 32 cores, which I don't think I've heard any other runtime being able to accomplish this feat yet. So congratulations to the people that worked on that project, as well as that these asterisks actually show some code changes or proposals that went into these specific versions, and the single asterisk means that it's a warning on this version, and that the two asterisks means that it's actually a real error in that version. So here are two changes that actually were code breaking, and this has happened quite a few times, and actually will be continuing to happen. But if you actually look at the migration guides for the for these version changes, they're actually quite small, even though the underlying changes to the compiler have been quite big and actually very important. But I don't want to dwell in the details right now. My point is that the Haskell community is very pragmatic, in the sense that when there's going to be breaking changes, it will usually have versions that are only warnings, so that you can change your code before it's an error, as well as that the Haskell community is still not afraid to change the language if, say, it's necessary, like the AMP and the BBP, which are I think are fantastic things that have happened in the Haskell community. So one of the topics that I'll be going back to in this talk is the concept of a domain-specific language. And so if you're from a Lisp persuasion, you'll know exactly what I mean. But what I mean by a domain-specific language is a language which is specific to the task that is to be solved. And what I mean by that is that, so here's an example. And here's an example for moving a robot hand. So you can rotate sockets, you can pinch and release the hand. And what this allows you to do is that when you've restricted the domain of possible expressions that you can create in the language, there is a wide variety of bugs that can't happen. So nowhere in here can I create a stack overflow or a buffer overflow or a cross-site scripting vulnerability or anything like that, because the constructs that would be available to programmers that create these vulnerabilities are just simply not present. The only operations that I can do is rotate, pinch, and release. And so I'll be coming back to this idea quite a bit. So let's go back to school. I'm really not kidding. We're actually going to go through some really simple examples just to quickly show off some features. This is going to go by really quickly. Don't worry about if it's confusing or not. This is just to get you ready and prepared by throwing lots of code examples at you. So, okay, we're going to implement Fibonacci because, every single beginner tutorial to programming, you obviously got to do Fibonacci. So, Um, it's not very difficult. Here's both ECMAScript and Java. Those are the implementations, and they work. And one of the things is that both of these implementations, if you saw, they are both recursive. They actually call themselves, right? And you know what that means? Well, you know what that means. That means a Stack Overflow. That's really bad. So that's if you've ever encountered that, you know that is a not very fun place to be in, and having to unravel recursive functions is just will make your day, I'm sure. And here's the honest-to-God implementation of Fibonacci in Haskell. It is actually a single line. And don't worry about what all this means. It may seem a little scary. It's actually really not. It's quite simple. But what I want to show you is that we have scanl here, and it's a function that accepts 3 arguments. And I'd like to point out that you're taking both plus as the actual function, so this is a higher order function, which is taking a function as an argument, and that it's also taking itself. So the definition is also being passed into scanl. And these are very common features in Haskell programs that, and as you can see, this is a recursively defined function. And the great thing is that not only does it create an infinite lazy list, it is also arbitrary precision, and it doesn't Stack Overflow. So yeah, less lines of code works even better. It's great. And yes, just to show that these are higher order functions. These are actually taking plus as an argument. But so just to be a little bit less scary, here's actually fibs in another way, right? So this is actually a more traditional definition of fibs, right? And this is obviously a 3-liner instead of a 1-liner like the last example. It's not as fancy because it actually is not an infinite lazy list anymore, but that's all besides the point. So, obviously if we get a 0, we return a 0. If we get a 1, we return a 1. If we have an n, then it looks exactly like the definition of fibs right in your textbook. And yes, it is that simple. And no, it doesn't Stack Overflow. And yes, it is arbitrary precision and all sorts of other neat things like that automatically for you. Yeah, and so in this previous example where we had this infinite list, if we were actually to use this example in JavaScript and we were to call it a whole bunch of times, it would actually have to recalculate fibs every single time, and recursively every single time. So if we actually wanted an implementation that was more equal to these in Haskell, we'd actually have to write an explicit cache and save the values in the cache, and it still will integer overflow. Don't forget that, because this is actually written over, if I remember, doubles. This is an arbitrary precision, so it'd be even worse if this was with arbitrary precision map, and the fact that it's doing arbitrary precision map in ECMAScript, just please, just stop it now. Don't worry about it. You don't even have to think about it anymore. You have Haskell now. Come on. So what I'm trying to get across here is that you have to use the right abstraction, and that there's no golden hammer. And I'm actually going to go backwards on that all of a sudden and say that probably the closest thing that I've ever found to a golden hammer, and it's not a golden hammer, is purity. And so to go through these points again, finding the right abstraction is very hard. And so to some people, this would be the right abstraction. This is actually literally the definition of fibs. But I wouldn't want to show that. I would want to show maybe something like this to someone who's never seen Haskell, right? This would be the right abstraction. And so finding the right abstraction is very hard. So it's all on viewpoint and who you're working with. And that, again, there is no golden hammer, and that it will always be a combination of features that makes something that is useful. And purity is actually the closest thing, and it will have to be coupled with discipline mutations, so when they're absolutely necessary, and domain expertise, knowing when to do those discipline mutations. So, but it's not that hard. You'll be able to figure it out. So let's keep going. Factorial. Wow, that looks exactly like the paper definition, I have to say, where you have this notation, and you might have seen this in other programming languages, which is creating a list from 1 to n, where this is being passed in. And then you're just taking the product of that entire list. Yeah, I like it. Greatest common denominator. So obviously, both of these could be rather nicely implemented in JavaScript or Java, whatever you'd like. But I just like to show how nicely these map between the paper definitions and the actual definitions. And I'd also like to show that actually this special syntax where you put these ticks on both sides takes a prefix function and makes it into an infix function. So that's a nice little trick just to kind of make it look more like the paper definition. And, for comparison, here's greatest common denominator. Yeah, I love writing my curly brackets and my if statements. Yeah. Here's Ackerman. I'm not even going to put the implementation of Ackerman in JavaScript. Don't you can go look it up. Okay, so here's finding roots. You remember that algorithm of finding roots of a function from high school? I just don't worry about the details. Here's some arbitrary function where we're going to find the roots of it, and we pass it in. And what I'd like to stress is that you have these very set-like notations, right? Where this is the definition of the even numbers, where you have a is a set of the integers, and there exists a p such that it's in the integers, and that a is 2 times p, right? That's even. And so you have this kind of similar notation, and this, which I actually spoke about, Python inherited certain features out of this notation, where you can create these set operations over lists. Very interesting. Don't worry about this. We'll come back to it. All right. Who's heard about Fermat's last theorem? Anyone? All right. We got a couple of people. So we'll take a look at how we can actually supposedly solve Fermat's last theorem using Haskell. So let's take a look at the wonderful Quick Check library. You may have already heard of it. It's a testing library, but it's different from most unit testing libraries in the sense that it's a property-based testing library. So you actually pass a property, right? And this is simply the identity, where given an S is equal to itself. And a Quick Check will generate 100 randomized tests to see that identity passes in Haskell, and it indeed does. And we can take a more complex example where, say, S is a list, right? And if we reverse it twice, it's the same thing as doing nothing to it. And Quick Check will actually automatically infer that from the reverse that we are checking over lists, and will generate 100 random lists to check for our function. Fantastic. So here's actually Fermat's last theorem encoded in Quick Check. So given an x, y, z, and an n, if the n is bigger than 3, then we will have the property that x to the n plus y to the n is not equal to z to the n. And this is actually a lie. This will actually sometimes fail. And I'd like to show that green is comments. So, and this is a lie, and this will actually sometimes fail, right? And we can look at, okay, so there is an example which failed, where x was 0, and then these two were the same, right? And that would make sense that would work. And so we have to actually constrain this even further, where we would actually say that all of these are not equal to 0, along with n being greater than 3. And now this works. And so, yeah, we checked 100 random cases against Fermat's last theorem, so thus we proved it. Right? Right? No. Alright, so my final back-to-school example. So here's integration. Actually, this is not only integration, this is integration using Simpson's rule. And if you know what this means, you are probably looking a little bit like this. Very happy. If you don't know what this is, don't worry about it. But what I'd like to show is that actually here is a feature that I'm going to show you where you see these dollar signs. All this means is that a parenthesis starts here and then that there's quote-unquote it goes as far as possible to the end where it can parenthesize, right? So this parenthesis will go all the way to quote-unquote the end of the line, right? And same here, right, where you have these that will be parenthesized. And another thing is that I'd like to show the map function. So what map does is that we have this function named g that we defined, right? And what map does is that it applies g to every item in that list. That's what map does, right? And this is what's known as a higher order function, and we already talked about these things. So it's actually map takes a function as an argument, and it applies it to everything in the list. So here again is an example of using very complex examples to illustrate points that I think are important. And so this is, yes, integration by Simpson's rule. Very cool. And this will be in the code examples, so please play around with that. And so, yeah, Haskell is supposed to be a statically typed language, but yet there wasn't a single type in any of this code. Actually, we'll go right through it. Not a single type, other than obviously the types in the Java programs, right? Not a single type. And so the reason why I mention that is that I like to say that the reason why this is because of type inference. Type inference will take your code and will, like it says, infer the type of the return, or actually not only just the return, but the entire type of the data or the code. So very big win. Although I will be introducing types right now. So here's a good old map. I introduced it 2 slides ago, right? Where right here, right? And where it took 2 arguments, right? So map takes 2 arguments, where it's a function from A to B and a list of A, and it returns a list of B. So we can see right here, very simple, where +1 is applied to each item in the list. We get exactly what we expect. I hope this is completely trivial. And what I'd like to stress about this is that there's actually another way to think about map, is that not only is it a function from a function that takes a function and a list of A and returns a list of B, but that it's a function that takes a function from A to B and returns a function from list of A to list of B. And this is because you can partially apply functions in Haskell, and we'll get to that very soon. So if we have this function, we can take a look at its type. So this is actually in the REPL, the command prompt that comes with Haskell, and we can take a look at the type. This is what this :t does, is it takes a look at the type of this function, and we can see it's from takes an int and returns an int. And this is a lie. We'll get to that very quickly. And we can see that map, if we apply map to that, it now says that it takes a list of int and it returns a list of int, right? So it kind of lifts a function up into to work over lists. And so the truth of these functions is actually, right, this is the actual type of the function. It's actually very similar. We're actually just saying that A is some sort of number, and that it's, from A to A, right? And then A is some sort of number, but it's from list of A to list B. So this is the actual function. It's more polymorphic than just int. And I hope that that is very clear. And like I said, the reason this works is because of partial application. We take this function and we make it work over lists. Alright, so let's get some more types. So I'm just going to throw a lot of definitions of types at you. And the most important thing about Haskell that is very different from other programming languages is this concept of sumtypes. Sumtypes. And this is similar to sums and products in mathematics. There's actually some very deep things that we'll be going into that pretty soon. Very interesting. And so we can take a look at this definition and say that Booleans are defined as either true or false. And this is the actual definition in the base library of Haskell. You can take a look at that. And we could also say, for an example, we have, say, a movie rating website, right? And you can have 1, 2, 3, 4, or 5 stars, right? If you think about how most people would represent this, they would actually represent this as maybe some sort of integer, right? Where you're using possibly billions of states to represent 5, right? While this is the actual simply 5 instances of this type, and only these types can be used to inhabit this type, or these instances can only be used. And then there's some other definitions that are more complex that we will get to pretty quickly, but let's not worry about that really quick. So a quick detour to pattern matching. So here's the definition of bool that we saw from our last slide, just the same. And we're actually going to define if as a library function, and we're simply going to pattern match over it. So if there's a true passed in, then just return the true part. And if there's a false passed in, then just return the false part. And the underscore is a wildcard, and that says to Haskell that you're not going to use this value and you don't want to give a name to it. And actually, you can actually set an option on Haskell where it will warn you about, say, if you do give it a name and you don't use it, it will actually warn you and say, hey, you gave this a name, but you haven't used it. So, very nice feature. And it works exactly like you think it would. If you pass in false, you get the false part of it. Very simple. And just think about it. We defined if at the library function. Now, there might be some of you who say, haha, I've done that before, but there are very few languages where it is, this could actually be a one-liner, but this is a two-liner for defining ifs at the library level. I think that's pretty fascinating. So, alright, let's look at the second very important data type. So, here we have the definition of maybe A, or just maybe. And it has 2 instances that can inhabit it. Nothing or just A, right? And we can take a look at some examples of that. So we can take a look at the type of just maybe, right? So this is some string that's being wrapped by this just, right? And the type is, as you would expect, string. We can obviously do some functions over that, where if we pass in a nothing, we get a string called nada, and and then if we get some sort of just, we can then show that thing in there. And it works really well, just like pattern matching. And the other one that complements maybe is either. And so this now actually uses 2 type variables. So see, this only used 1 type variable. This now uses 2 type variables, and there's, just like maybe, 2 instances. But they're named differently, and instead of having nothing in it's left, and it actually holds a type. And usually what either is used for is like nothing, or like maybe, where you can have some sort of failure case, right? But there's also a error message held in the failure case, right? So we can take a look at the type, and we can see that the type of this expression is either string B, because we haven't given a concrete type to it for its second constructor yet. So there you go. And the third type, to kind of wrap all this up, is these. And so this also has two type variables, but it has three instances where you have this, that, and these, where this holds A, that holds B, and these holds both of them. This might be useful sometimes. I've never personally had to use it in any of my code, but I could see that this sometimes could be useful. It's a very interesting semantic middle ground. Alright, so I don't know any other programming language that would allow you to build a calculator on a single slide. So here we have an expression that we're defining, and it can have an integer, a plus, minus, multiplication, or division expression, and we can then write an eval function for it that simply unwraps the integer if it gets it, or then recursively evaluates each branch and just uses the internal Haskell operators. And we can evaluate some expression, and it gets exactly what we expect. And this is definitely not operator overloading. This is actually creating very similar to a domain-specific language for a simple calculator. These can also be defined prefix, right? So we pull out the internal part, and looks exactly the same, maybe a little bit more verbose. And then we can also take an additional step, and it is even more verbose, but we can actually pull out the operator and just define it by itself, and then have just the expression. So this actually deduplicates this part of it, right? And this is actually, there is a good reason to use this. This is actually a much easier way to do parse, if you care about parsing, where you have kind of a hook, and then you have this operator. It's much, even though it is more verbose when you're constructing the AST, it is much more easier for programmatic control or manipulation of the AST. So, and here we go. Look, do you remember this example from DSL a couple of slides ago? Well, here's the definition of that language in a data type. So we can look that a robot program is a list of robot commands, right? And a robot command is either a rotate, a pinch, or a release, right? And a rotate has a socket and an integer. A pinch has a hand, and a release has a hand. And say we have 3 sockets and 2 hands, if you want to, right? And there we go. That is essentially the definition of that programming language, that domain-specific language, in a data type. And we can actually show, I just want to show really quickly, one of the things that Haskell lets you do is so this is an integer and this is an int, right? And so the int is actually a low-level machine-level integer, so if you know that you will never get out of the bounds of a machine int, then go ahead, use int. But most of the time, you're using integer, which is actually the default, and that's an arbitrary precision integer. So something you should know about, int and integer. Here, both are available. And there's a lot of low-level ones as well. Obviously, there's the typical double and float and all those things, but then there's also even lower-level representations if you really need to do that. And so now we can take this program and we can actually transform it into a actual Haskell data type. We'll just define RC as a list that contains these constructors, right? And we can take a look at the type of RC, and this is actually a lie. What Haskell tends to do is actually infer the most general type. So this will actually show robot command instead of robot program, or list of robot command instead of robot program. So, I mean, they are essentially equivalent, just Haskell doesn't always use the type synonyms that we provide it. So, but they're essentially the same thing. And so as you can see, I'm just squishing all of these types over to the side right here. We're just squishing them over. And here's an eval function. So we made an eval function for arithmetic. Now we're going to write a little eval function for controlling a robot. Or, well, really it's just going to show some strings. And so let's take a look at this. Let's piece this together. So probably the most interesting thing is, this comes in and we get this string. And here's it actually working. So we get this string with new lines, and it'll yell out rotating socket 2 by 90, pinching hand, etc., etc. And what this does, that string comes in, and then it'll separate it by lines, and then it'll read each of those lines, right? Because we're mapping reads over each of those lines, right? And then what that does is then it will map M, and don't worry about this. This is just being able to map an effectful operation, which this is, over this list, right? Map and map M are extremely similar, exactly the same essentially, just with different types. And essentially what run robot does over that list is that it will show this function that takes in, either a rotate, a pinch, or a release, and then yells it out, right? Deconstructs it, shows it, concatenates it. These pluses are concatenation. And it works exactly like you would expect. It's cute but not scalable. You would not want to do this in production code. This is just something I created to put on a single slide to kind of show how powerful Haskell is. So there's much better ways of doing this, and I'll talk about more of that in the second presentation. And what I really want to show here is that unlike most other languages, we're actually using lists as control structures. So we're actually using a list as a sort of program that is then passed into an evaluation function. And this is a very common, I'd hate to say the word pattern in Haskell, where you create a little miniature domain-specific language and that you use lists of these expressions as a program, or some other data structure where you're kind of using data structures as the control structures, and the functions are simply just mappings from input to output, just like they are right here. So, and exactly like I was saying. So, like I said, thinking programs as static mappings from its input to its output and the data controlling the execution, instead of thinking as the code controlling the execution of a piece of static data. Because this is how I visualize programming these days, is that the data is constantly changing out there. That you want to have this reactive system that will be able to change based on new information, and this it takes this information and it maps it to some output, and the data controls the execution of this program at runtime. And this is completely different than the standard OOP programming, where you have some sort of state machine, and the code controls the manipulation of some data. This is a very different way of thinking about programming. And so just throwing in more details about Haskell, Haskell does this really neat thing called exhaustive disk checking. So we will define this random arbitrary type with 3 instances, barbags, quucks, and we create this pattern matching function over it that at some point we forget the quucks part, right? And what Haskell will do is that it will actually yell at us. It will say, hey, this function is not exhaustive. It does not exhaust all of the possible inputs, and it will essentially yell at us at compile time. Not at runtime, but at compile time. And we can, obviously add the third case, and it will work perfectly fine, and it won't yell at us anymore. And this is a big win, because if you have a maintenance problem where, say, you have a very big program, and you're creating a change to some very core internal data type where you're adding say another constructor, and what will happen is that at every point in all of the code, Haskell will see that all of these functions are missing this case, and it will highlight every single one of the cases in which your new constructor is missing. So very massive big win on maintenance. I cannot stress how important this is. Alright, so I keep taking you guys back to high school, and I'm going to keep doing that. So if you guys will remember from high school, f of high school mathematics, f of g is equal to f dot g of x, right? And so this is what we were originally shown in high school, and actually Haskell takes it one step further and will simplify this entire expression to just this. And to show that, we can take a look at this, right? Where we have f is plus 2 and g is times 2, right? And all three of these functions are equivalent, right? Where if we take f of g of x, that's the same of f of g of x, and that's just the same as f of g. And I think that this last one is the clearest of all of them, because this is not saying that j is a function that accepts x as an argument and then passes it into this. Instead, what it is saying is that j is simply a name to this operation, and you can apply j to some sort of piece of data, right? So that there's a direct one-to-one mapping. And the reason why you can actually remove these x's is because of further algebraic simplification, essentially. And very big win. I just want to show you that you will tend to see a lot of Haskell code written like this, and this is really fantastic. Point-free style is what they call it. And so what I, again, just want to reinforce with this $sign, if you don't remember, this does parentheses all the way to as far as it can go to the end. So, all right. So let's look at the definition of lists in Haskell, and this line right here is the actual definition of a list in Haskell. This is, if you looked in the base library, this is what you would see. And let's piece this apart, actually. So list takes a single type variable, and it is either a empty list or a variable appended to the rest, some recursive list that eventually ends with nil. And if you were of some Lisp persuasion, then this would actually read more like nil and cons with a list, right? And I just like to show you that this is the infix version. You can actually make this a prefix version, so this actually lines up a little bit better. It's exactly the same, except this is just kind of a little bit nicer because Haskell has some syntax sugar to deal with lists. So, but that's the full prefix version. And just to show you that not all of these data types have to make sense. So here's two weird lists, right? Weird list 1 and weird list 2. And they take actually two type variables, right? And so it can be either a nil or a cons, right? And it looks exactly the same until we get here, where we actually notice that the first item will be an A, but then everything else will be a B, right? If you can kind of see what that does. And the second one is either a nil or a cons, but as you can see, it weaves the two arguments. So in the first one, it will be an A, and in the second one, it will be a B, and in the third one, it will be back to an A, and the fourth one will be a B, and so on and so forth, basically weaving back and forth. And the interesting thing is that actually the type system will enforce this invariant. So if you actually try to construct an instance of this list that does not conform to this even odd back and forth of types, then it will actually fail at compile time. So very interesting. So more on lists. We've seen a lot of this stuff where you can define a list, and all three of these definitions are equivalent. This is just the fully explicit definition. As you can see, there's the empty list at the bottom, and then it constructs on top, on top, on top. And you can also create infinite lists, right? So this is 1 dot dot dot, or dot dot. And we can also create, say, a list of odd numbers, right, by creating a stride where the stride skips 2, right? So it goes 1, 3, 5, 7, 9, and creates a list of odd numbers. And obviously this can be infinite. You can also append, say 13 onto this list, or you can also concatenate these two lists, right? And I just like to show you that these two are actually equivalent. So just like in the example where we turned a prefix function into an infix function by appending little ticks on both sides, you can actually create an infix function, which this is, and you define that by having it with parentheses, right? So having any function that has parentheses on both sides creates a infix symbolic function, essentially. And so this is just the prefix version of this infix function. So you'll see that again and again. You can take the head of the list, obviously. You can take the tail of the list. You can take the first 5 elements of an infinite list. And the important thing about this is that it will only actually ever calculate the first 5 items, right? This is one of the great things about laziness, is that you can define an infinite list, but because Haskell is lazy, it will only calculate the items that are asked for. So it will only calculate the first 5 items. We can drop 3 items off of a list. We can take the length of dropping 2 items off of the list, and you get exactly what you expect. Can append 0 to mapping, etc., etc. Get exactly what you expect. You can also have nested lists. So here's a list of lists, right? And the type of that is exactly what you would expect, a list of integers. So thunks, as you can see, I love thunks right here. I really do love thunks, and they are awesome. So the reason why they are awesome is because if you were in a strict language, if you define x as 2 plus 2, it would instantly be evaluated as 4. While in a lazy language, if you evaluate x as 2 plus 2, it actually will evaluate to a thunk that holds the value, or the computation. This is how laziness works, is that essentially any definition that you make will define a thunk. And then what you do is that you force that thunk. And it evaluates exactly how you would expect. And note, this is pseudocode. This is actually isn't how it works in Haskell. This is just an example showing that how it works underneath the hoods, but this isn't actual Haskell syntax or anything like that. It's pseudocode. Some more info on map. So again, here's that algebraic simplification where we have L on both sides, so we can remove it. And this makes it much more clear that 1 is simply the name of this operation of mapping times 2 over something. And again, we're taking a look of map lifting this function up into lists, right? So it takes a function and it lifts it into the realm of lists. And obviously that's a lie. That's what it is. And just like I said, this would be an infix function, but you can make it a prefix function by putting parentheses around it, and it works exactly like you would expect. Kind of a little weird, but makes sense. And then what you can do is, since we defined this 1, right, as map times 2, it works exactly how you would expect. You're just getting everything in the list multiplied by 2, and it works exactly like you expect. And like I said, I'm just stressing this point that map lifts a function from a regular function into a function that works over lists. And we've seen these already right here with these num, and as well as quite a few of these other ones. And what these are known as these are called type classes. And you have this constraint, right? So this is a thick arrow and this is a thin arrow, right? And these thick arrows essentially section off these constraints away from these type variables. And there's a lot of these. And this is a very core feature of Haskell. And no, type classes have nothing to do with classes in object-oriented programming. It's completely different. So now I want to introduce foldl and scanl, because we'd actually seen these before in previous examples. I didn't give quite a lot of attention to them, but they are very important. And this is actually a partial lie. These are actually the types of them. I'm just going to make it a little bit more simpler, so I'm just going to turn all these B's into A's, just so that you can see that the structure is very similar, although the A's and the B's do matter. So, and this is a total lie. This is completely a lie. And the examples right here kind of show that they all, as you can see, kind of take similar arguments, but they do different things with the exact same arguments, right? So, and the L and the R, as you kind of expected, are left and right, right? So where you're folding from the left and you're folding from the right. And as you can see, sometimes they'll do the same thing, but sometimes they'll do opposite things, right? And what fold L does is that it essentially takes this function and then it puts it in between each of the items in the list, right? And what fold R does is that it does it from the other side, right? And what scanl does is that it does exactly the same thing as fold R, but it saves all of the intermediate values. So, as you can see, doing a scanl or a scanr reverses the list, right? So, as you can see, this is 0 plus 1 plus 2 plus 3 plus 4 plus 5, right? So, and the reason why all this is important is because, so see, if we change these, right, and we now did a division by 1, if we do it from different directions, see, you get very different answers. And so this was a lie. This actually was the truth only a couple of months ago, but this is actually now a lie, and this is actually the truth. It's a little bit more complex. Instead of being defined over lists, it's actually now a bit more polymorphic. It's defined over anything that's foldable, right? And lists have a foldable instance, so it works all very nicely. And so if you remember sum and product from our definition of factorial, these are actually just defined in terms of fold L. And these are the actual definitions in the prelude, the base library. And I'd like to show you that the reason why this works, and this may be a little technical, but bear with me, is that fold L and fold over sum and products works because the integers form two different monoids over plus and multiplication with the identities as 0 and 1 respectively. And very deep theoretical stuff, monoids are your friend. And just wanted to mention that, so we'll talk about this a little bit later. And so we already saw map, length, and append. So here's the actual definitions, and yes, these are the actual definitions that are in the library. Let's go through them really quick. So obviously, if it's an empty list, just return an empty list. And if you get an F and there's an X with a whole bunch of other X's, then just apply F to that first X and then map the rest of the list, right? Very simple. That is the definition of map. As well as length, if the empty list case happens, then it's 0, and then if you have the rest of the list, then just add 1 to the rest of the length of the list. Very simple. So append works again. Again, all three of these are pattern matching off of an empty list. You usually, that's a very common thing to happen. So if it's a empty list, then just return y. And then if there's the rest of the list, this is a little bit more complex, but just append x to the concatenation of x's with y's. And eventually x's will run out and become an empty list, and then it'll just return y's, and ta-da! Yes. So list comprehensions. I actually already showed this to you earlier with fold roots. And so I'm just throwing some examples at you. These essentially have a whole bunch of different ways that you can create list comprehensions. If you've used Python, then you probably know what these are. I'm showing that actually you can create equivalent definitions with filters. So this one is actually just a filter. So there's many ways to express the same computation using either list comprehensions or some higher order function. And then, whoops, these are a lie, this is the actual type, who cares? As well as that I'm just reinforcing this algebraic simplification that you can do, where you can remove the ES's. Very fun. And filter works exactly how you would expect. It takes a function from A to bool and a list of A, and then returns a list of A with all the things that met this filtered out. And it looks very similar, as you can see. Alright, so depending on your background, you may have seen tuples, you may have not seen them, but you can think of them as small little lists with a fixed number of elements. So lists have an infinite amount of elements, obviously up to the machine limits, and tuples have a fixed number of elements, and they're actually reflected in the types. They're also heterogeneous, so as you saw, by definition, lists are homogeneous, as well as that tuples are immutable, and they are true random access. So let's take a look at them. So here's some examples of tuples. So you have a 1 with a string, you have a float with an integer with another float, or you have a string with a list, so you can actually have lists inside of tuples, as well as that you can have lists of tuples or tuples with lists inside of them, right? And if Haskell didn't have tuples, you can actually quite literally define them. So there's two definitions, a 2 tuple and a 3 tuple. Just Haskell has nice syntactical sugar for them, and I'm pretty sure this is actually very similar to how they're defined internally. Actually, it is. This is very similar to how they're defined internally. And you can take the first item in the tuple or the second item in the tuple. Very simple. And you can also create, again, like I said, crazy tuples like this. So this is how tuples are defined, but this is me just introducing even more things as I'm introducing other things. So as you can see, this tuple has a phantom type, where there is a type that appears on the left-hand side that does not appear on the right-hand side. So that's very important. Again, you can get pretty arbitrary with these kind of things. So just if you have some sort of invariants that need to be met, it's very easy to simply define them this way. And you can write functions over tuples. So here's a weird tuple function that deconstructs a 3 tuple and then returns a 5 tuple with some items messed around and some addition, and this is how it looks when it's called. This is called a destructuring bind. Then there's zip, which takes 2 lists and then returns a list of tuples, and it does this pairwise. So we can see an example where you define A through C and you zip it with an infinite list, and zip will always end on the shorter list, and it creates, it zips them together, right? A, B, C is with 1, 2, 3, and obviously if you flip the ordering, then the ordering will also be flipped between the two, as you can see. Alright, lambdas. So you might have seen these in other languages. Actually, I already introduced them already. Very simple. It just is also known as an anonymous function. They take an argument, and you can define a function, and then you can apply it to some arguments, and you can write them over 2 arguments and apply them to 2 arguments. There's an interesting generalization of lambdas called vow, and their vow calculus. Very interesting if you're interested in the more theoretical side of things. So lots of fun stuff. And then there's these things called sections. We've already seen them before. They look like this, where you have these parentheses, right? And they are essentially just like lambdas. They're actually essentially syntactical sugar for lambdas. And so here's some equivalences, right? So you can actually have, and it gets confusing, sections of compositions. You can also have tuple sections. Lots of fun to be had there. Very concise code to be written. Alright, so we saw sum types, so now we should see product types. And so product types, we've actually already seen them. Think of structs, tuples, and records, right? Haven't talked about records yet, but we'll get to that. And well, this is actually what we're doing, records, right? So okay, so we have this this kind of struct, right, where we have these fields that are named and they have some type that inhabits them. And we can, construct it, right? So we're constructing PT with its 2 arguments, and we're grabbing the one called 1 out of it, and we get exactly what we expect. And this is the more explicit version of these 2. This is actually the positional definition, while this is the explicit definition. So there's actually nice syntactical sugar for defining records. Very nice. As well as that, if we look at the type of each of these functions, see it takes a PT and returns an int, like you would expect, and this takes a PT and returns a string, like you would expect. So there's really no magic behind these whatsoever. And we can have a lot of fun, right? Where we can now add some type variables, make them a little bit more complex, right? So now PT takes, 1 takes a PT of A to B and returns an A, and 2 takes a PT of AB and returns a B. We can take a look at the type and now see they're inhabited. Instead of being just type variables, they're now concrete. So works very, very nicely. Also, I'm trying to show you that type variables are not the same thing as fields, right, or accessors, right? So you can have, this record, and then I can just add an additional field to it while still having these, and we can take a look that this takes a PT with type variables, but returns a concrete type, essentially string in this, and you can take a look at the types, and it all works. And then here's some functions actually that we can define. So let's actually just define PT as this, right? And then if we define these 2 functions, and what you see here is that actually these actually do exactly the same thing, right? You can see that this is true, that oops, sorry about the typo, that should be PT. These 2 things are exactly the same, and they're just defined differently, where this one is defined positionally, but this one is actually where this is called a record wildcard syntax, where what this does is that it takes all of the accessors that are in the record and it brings them into scope inside of this function. And so we could just say this is 2, and this does exactly what you would expect. As well as that with record wildcard, the extension, we can actually pattern match off of the values inside of each of the accessors. So as you can see, if PT has a 0 inside of it, it will return the 2 field. But if it has a 1 inside of it, it will return the 3 field, right? And so since PT has 1 inside of it, it returns 3. Because we're pattern matching over it. I hope that makes sense. And so now I'd like to talk about new types. New types are just like records, except that they have only 1 field, right? That's the restriction with new types, is that they can have as many type variables as they want, but they have to have only 1 field. So this has 3 fields. This can only have 1 field, and obviously you can swap them out. The thing about new types is that they are erased at runtime. So they actually have no cost at runtime. And what you use them for is here's the example I'm going to get to. They work exactly like records. I just want to point out. So I'm not going to go over this in exhaustive detail. They work exactly like records. And the thing about new types is that they are erased at runtime, and see, we have an example here where, say, we have usually a user ID and a table ID, and they're usually represented as integers, right? But we can wrap them inside of a new type that will be erased at runtime, but at compile time, say if we write a function that takes a user ID and does something like return a string, at compile time, if we try to pass in, say, a table with an integer inside of it, it will actually not compile. It will be a compile time error. So this allows for very strong levels of type checking, so that you can't mix up these kinds of IDs just by a bad keystroke or something like that, the compiler will enforce these invariants. And like I said, completely free at runtime. These will be actually erased at runtime or at compile time, and they will be represented as machine integers and nothing else. So very nice. And so we're going to get back into sums again, right? And these are also known as coproducts. And if you remember from the previous examples, here's some of the examples that we saw. And the reason why they're called sums or coproducts is because they are essentially the mathematical dual of products or records or tuples or whatever you want to call them. In the sense that instead of gluing things together, you're actually saying that these are the only possible separate instances of a certain type. And what I'd like to show you here is that actually the product types are very similar. So here's the definition of a sum type, and we can define it either positionally as a tuple or as a full-on record with accessors, right? So these are all equivalent essentially, except that this has more power because it has accessors, and this has functions that can work over tuples, while this is simply just positionally, right? So you were having a product inside of a sum, or a product inside of a coproduct, as they like to call it. And the reason why they're called sums and products is because they have very important mathematical, actually algebraic properties. And if you want to know more about these properties, you can take a look at this blog post. But in short, what this allows you to do is to do some algebraic simplification. So where this is equal to this, right, where you're pulling out this A outside and leaving this B and C alone, right, where here this A is being duplicated here, but it's not being duplicated here because it's been pulled out of the second one, right? Where you're pulling out this A. And so this property of sum types is actually exactly equivalent to the property in high school algebra that we saw. This is very important. And actually, we can take a step further and say that this is either, this sum BC that we defined is actually just either. Right? I hope that makes sense, right? And that actually, if we wanted to go even further, sum 2 can actually be defined in terms of either, right? Because this is a product, right? And we're just saying that this is a sum of products, right? And that's what either does. And this is actually just a type synonym. This is actually no longer a actual type definition. This is just a type synonym over either. I hope that makes sense. Alright. And there's exponents and quotients too in terms of types, but I'm not going to talk about them. Please go check them out. They're really fascinating, but they're not used as much as I would hope they would be. So, alright. Now let's get on to kinds. Kinds are, the easiest way to talk about them is that they're the type of types. And to talk about them a little bit in more detail, they allow you to reason about the saturation of your constructors. And they're really not in many other languages other than Haskell, and I really miss them in other languages. This is actually a very important feature of what makes Haskell so great, and actually so much better than languages like, say, Scala, which try to pretend to be like Haskell, but yet they don't have kinds. So here's a very simple record that we have defined with 3 accessors, and it's obviously defined over some type variables. And we can take a look at the kind. Just like we were taking a look at the types, we can take a look at the kind of this. And as you can see, because this accepts 2 type variables, it has these stars here. And a star means that it's fully saturated, right? So if we pass in an int, then it still is waiting for one more. And if we pass in that final string, now this type is fully saturated. There are no more variables to be filled with concrete types. And now if we play around with the record, say we remove this record and we actually now make this some sort of type of A of B, right? This now actually shows up as being a higher order type. And now a simple type such as maybe could not fit in anymore. Or sorry, such as int could not fit in, and you actually need a type of maybe, because a maybe is of kind star to star, right? And that's what fits in. Because if you try to put in an int, it would say, no, ki should have a kind star to star, but int has a kind of int, or a kind of star. Sorry, I'm messing up. So I hope that just from the error message that ki is expecting something of kind star to star, but int has a kind of star, right? So maybe is an example that works here. And then we just fill in something like string. Int would work here too, right? Because it has a kind of star, and that's what it's expecting. So there we go. And we can take this one more step further. So say we add even a third type variable, right? And we have a third type variable here. So now the first one is kind star to star to star, right? And so if we tried maybe, just like we had right here, right? That would actually now break, right? Because now it's expecting a kind of star to star to star. But maybe only has a kind of star to star. So we would actually have to put in something like either. And either would work here, right? And now it's ki either string. And the other thing that would work here too is these, if you remember. So we had maybe, either, and these. And because these is a kind of star to star to star, then that would work here in place of either as well. So, all right. Type classes 102. So here's so equality is one of these type classes that we talked about, as well as show, monoid, foldable, all these other ones, right? So here we're defining a data type, right? Some type with these instances bar, baz, and quux, and we can create an instance of equality over this type of foo, right? And where we're saying, okay, if its bar is true and true, I think that's quite clear, right? But if you remember from OOP, this is actually given to you, quote-unquote, for free, right? Where each object comes with its own notion of equality and hashing baked into each object. And has that ever bitten you? Where, didn't you wish that some object had some other instance of equality, but it doesn't, where you had to create some sort of hack to get around it? This isn't a hack. This is actually how equality is defined across all sorts of data types. And so if we wanted to make some sort of even crazier kind of equality, right, where bar and baz were equal, then we could just add these cases. And we could even go even stranger, where bar and baz are only equal to each other if they're passed in this way, right? While this one, they're equal either way, right? So we can have very fine-grained notions of equality that we can define very easily, actually. This is how it's defined. But if we're feeling lazy, we can just derive it. And this will automatically actually create this instance for us without having to have us type out that entire thing. So, very big win. As you can see, we can create some sort of instance of show that doesn't even have to look like anything that you would expect, right? You can create whatever you want, or you can just derive it. Very simple. And that would just derive exactly this. And you can also drive multiple classes, right, with this kind of tuple syntax. Very simple. And then there's functor. And what functor does is that it actually defines map. But you kind of see this, where it takes an A to B, and it makes a F of A to B, so this could kind of have like a list. Huh? Can you see that? Kind of looks similar, right? But that's actually what it is, right? And you can, so if you wanted to define a functor over maybe, then it would just be, if you had nothing, it would be nothing. Or if it was just, then you would just return a just with F applied to A. Very simple. So now this makes a function that is normal, but now works over maybes, right? Or you can make a these instance or an either instance for functor, right? There's all sorts of instances that you can create, and just like you would expect, the functor instance for list is literally just map. It's exactly the same. And look, we've done all this programming, all this data types, all sorts of functions, all without if then else. Well, actually, we did define if, but I didn't actually introduce the baked in if then else. And it's exactly the same as any other language, except the only thing that's different is that the else case is mandatory. And for good reasons. I mean, you wouldn't want to ever leave out an else case, because otherwise why would you be using an if statement? And there's other things like while and until. So exactly all the stuff that you would expect in any other programming language. And so let's go back to benefits of purity really quick, as I'm going to wrap all of this stuff up for the next presentation. So one of the benefits of purity is actually immutable data, and you may have already seen this with like virtual DOM and OHM, where you have a structure that you know will never change in the future. And so what you're able to do is to record the changes simply as what has changed, right? Because you know that the past will never change, so all you have to record is not an entire new copy, but only the things that have changed. And this is called structure sharing, or shallow copying. And this is very useful and extremely fast, especially when you have very large data structures that are having only very sparse changes done to them. And so the second thing that I'd like to show off, other than FP complete, is Haskell. And so this is another benefit of purity that I cannot stress enough. So say we have some function that we know the type of, but we don't know the name of, right? So here we go. Here's exactly what you would expect. We get map back, right? Where you have all sorts of searches that you can put in that will let you find the information about these things, and you can go straight into the documentation and then straight into the source code of the implementation, and it's very simple. No other programming languages has that. Only Haskell has this kind of very well developed search functionality over its code, and no other language kind of compares to Haskell and its abilities. So please check that out. I actually use Haskell constantly when I'm developing code, and when I'm in other languages, it's almost difficult to imagine the fact that I used to program without Haskell actually existing. So take a look at that. As well as that, with purity, you can have many different types of optimizations that can happen automatically without you having to lift a finger. So these two functions are equivalent, right? So if you map f over mapping g of x's, that's just the same thing as mapping f over, or mapping f of g over x's, right? These two are equivalent, but the second one is faster. The reason why is because you're only doing a single map over the list, while this you're mapping g and then you're mapping again with f. And this transformation can only hold if your functions are pure. Otherwise, you can't do this kind of transformation because it'll just break. You don't have the guarantees about the code that will allow you to do something like that. And so this is just such a massive win. And this actually means that the larger your code base gets, the more optimized it essentially gets, because not only do you have laziness, but now you have this stream function where the compiler is doing this massively complex transformation of your code into essentially so it takes code that has many maps over it and transforms your code into code that only has a single map. And the larger your code gets, the bigger a win this becomes. I really can't stress this enough. This is just amazing that it works so well. And, you know, Haskell isn't perfect. There's a lot of things in Haskell that could be better. And just to name off a couple, CPP, this is the C preprocessor. This allows, it's this really not really great string concatenation language that essentially uses the C preprocessor to do essentially compiler version comparisons and maintaining code over different versions of compilers. And it really sucks, but it's going to be around for a while, so you're going to have to deal with this. as well as that Haskell doesn't have the greatest module system, but Haskell, the GHC development team is actually moving forward with this project called Backpack that will be giving ML-style modules into Haskell, so it'll be solving a lot of problems that the lack of proper modules has had on the Haskell community. So really great. As well as that Haskell doesn't have dependent types, so that's kind of a pet thing of mine personally, although it has been moving in that direction with things like type-level naturals, so you never know, as well as that some of the default data structures kind of suck. So that example of a bad critique of Haskell was actually based on the fact that by default lists are linked lists instead of, arrays, and so there's a lot of things that can catch up a beginner, but the thing is that there's been lots of really big changes happening in the language, so this might become better. And as well as that abstraction isn't free, but it is nearly so. So Stream Fusion is an example of that, where essentially that kind of abstraction is cheap and made cheap, right? But there's still some abstractions that aren't exactly free, that can't be caught by things like Stream Fusion. So there are things in the works like a JIT for Haskell, or a full optimizing compiler, full program optimizing compiler for Haskell. But they're still kind of experimental. But either way, Haskell is so performant already that there's things in Haskell that could be improved that are more important than making abstractions completely free. So, and actually there's a lot of things that I can't put on this slide anymore because they've actually been solved. So there's that. Anyway, that's it. If you have any questions or maybe suggestions for future talks or clarifications, I'd highly appreciate them. So thank you so much for watching, and I hope you enjoyed. Thanks.